Hello everybody, this video clip is still on chapter 6, okay, but this one is the section 6.7. Previously on the single variable calculus, you have learned that if you have y equals to f of x, okay, then you can approximate your f prime x by the quotient of fx plus delta x minus fx over the difference between the input x, so which is the delta x here, or you can multiply this one over and then move this one to this side to have your f at x plus delta x, okay, is approximated by f at x plus your f prime x multiplied by delta x here, okay. And usually this one, okay, the f prime x with the delta x, usually it is the approximation of the so-called delta f, okay. And of course, I mean, the delta f is simply the difference between f of x plus delta x and f of x, okay. So for this section, we are going to again elevate ourselves to the two variable, or I mean at least two variable function, okay. And if you have your z equals to f of xy, then we are going to saying that the delta z, okay, came from the f sub x, okay, the contribution along the x direction, okay. I mean the same thing as we have previously. It is the derivative of f, right? But previously we have only one variable, okay, but this one you got two variables, so you have one contribution along the x direction multiplied with the delta x, okay, a small change in x, and another contribution along the y direction together with the delta y, okay, and you combine these two contribution together, okay. So it means that to approximate, okay, to do the approximation, if you have your z as a function of x and y, your delta x is a small change in the x direction, the delta y is a small change in y direction. The corresponding change in the z direction, which is the delta z, okay, so the delta z, it is actually the z of x plus delta x, y plus delta y, okay, minus z at the particular point xy, okay, can be approximated by, okay, can be approximated by the z sub x delta x and z sub y delta y, just like this, okay. Or I mean, sometime if you want to calculate this one instead, okay, sometime you may need to find this one. It is approximated by set value at the particular point xy and then plus the what, because this one you just move it here, right, the derivative of z with respect to x delta x and derivative of z with respect to y delta y, okay. So it simply means that if you have a small change in x, you got a little bit change in terms of x like this, and for a small change in y, that effect will be in the y direction like that, okay, added together. For example, okay, if a certain factory daily output in terms of 60 k to the 1/2 L to the 1/3 units, okay, and your k is a capital investment, okay, measured in term of $1,000, and your L is the size of labor force measured in worker hours, okay. Currently your investment is 900,000, okay. So I mean, when you see it like that, what is your k actually, okay? Your k, one unit of your k, it is 1,000, right? So this one is 900,000, so your k is actually 900, okay, be careful. How about your L? This one can be immediately your L, okay, because your L already measured in worker hours, okay. So this one is 1,000 worker hours of labor. Okay, so you are going to estimate the change, okay, in the output. So is the estimate the change in Q, so which is the delta Q, that will result, okay, if the capital investment is increased by a small unit, right? A small unit, which is 1,000. So this means that your delta K is actually your delta K is actually 1, because $1,000 mean 1 unit in terms of K, right? And your delta L is 2 worker hours. Okay, so this one just simply like want to approximate like how the increment in terms of capital and the increment in terms of labor hour together will affect the daily output. Okay, so as we have previously, the delta Q, okay, so the change here is the change in output, it is the delta Q. It is approximated by the dq by dk delta K together with dq by dl delta L. Okay, so what you have to find is dq dk. This one is not that difficult because it is 60 L raised to the power 1/3. This one is all constant, right? And then a derivative go directly to this k to the 1/2, which is 1/2 k to the negative 1/2. Okay, on the other hand, if you want to find the dq dl, okay, the dq dl can be found by, you know, this one 60 k raised to the power 1/2 is a constant, so the derivative with respect to L go directly to L to the 1/3, so you got 1/3 L to the negative 2/3. Okay, so you have it like this. So it means that your delta Q, okay, it is approximated by this one. What is it that you got? 30 L to the 1/3 over K to the 1/2 with the delta K. All right, and here you have 20 K to the 1/2 L to the 2/3 delta L, right? So now what's your L at this moment? Okay, so the L is the one that you have it at this moment. Your L at this moment is 1,000, so this one is 1,000 raised to the power 1/3, and then your K is 900 raised to the power 1/2, and then your delta K is a small increment that you want to increase. Okay, so your delta K now is only 1, right here, and then this one 20, your K again, it is 900 raised to the power 1/2, your L is 1,000 raised to the power 2/3, and the delta L that you want to increase is 2. Okay, then you just do a calculation. Okay, this one, after taking a square root, then you have a 30, so the 30 and 30 cancelled. This one, after taking the third root, you got a 10, so the first term you got 10, and then this one, after taking the third root and then find square, so you have 100. This one you got 30, so on top you got 600 over 100, so you have 6, so you have 12 here. This one you have 22. Okay, so you can say it can be said that the change in output, okay, so the change in output that will result if your investment increased by this much, and the labor increased by 2 hours is increasing, the change is increasing by 22 units. Okay, so again, this one is like for you to have the information to get to decide whether you want to increase the capital by this much or not, or you want to increase your worker hour by this much or not. Okay, I mean, if you do it by this increment of worker and this increment of capital, then this is the amount that will result, I mean, for the daily output that will increasing. Okay, however, I mean, you can see that right now the word increased is used, right? The word increased is used. You may use the word decreased as well. So if it is decreasing, then your delta, the increment, can be negative. Okay, it can be negative as well. So if instead of increasing, if you got decreasing, then this increment, the delta, can be negative value. Okay, all right. How about this one? This one, it says that if you have X hour of skilled labor and Y hours of unskilled labor, it can produce this much unit. Okay, this many unit. Okay, you have 10x y raised to the power 1/2. Okay, you see the factor of the unskilled labor, it like lower a little bit by a square root, right? Currently, you have 30 hours of skilled labor, so here's your x cost. Okay, and then you got a 36 hours of unskilled labor, there's your y. Okay, and they want to add, you see, increase, right? 1 hour of skilled labor. So this one is a small increment in terms of increasing, right? So this one is a delta x because it is a skilled labor, is a positive one. So let me just put positive to be exact, right? You want to estimate the corresponding change that the manufacturer should make in the level of unskilled labor. So here's the change of the unskilled labor. So it means that you want to know the delta y so that the total output remain the same. So this keyword, what does this mean? The total output will be the same. So if you increase your skilled labor, actually it will affect your output, right? So it should have your delta F as well. However, this delta F need to be the same, to remain the same. So your delta F must be 0. Okay, this is the setting. So what is the delta F right now? The delta F, again, it is approximated by df by dx, delta x, df by dy, delta y. Okay, so let's try to find the derivative of this function with respect to x. So you got 10y to the 1/2, and the derivative go directly to your x, which is 1, and delta x. How about a derivative with respect to y here? So you got 10x, and the derivative go to y to the 1/2, which is 1/2 y to the negative 1/2, and then delta y. Okay, so what is your x right now? Your x right now is 30, so you got a 10, and your y is 36, so your y is 36 raised to the power 1/2, and your increment in terms of the, delta x, it is a positive 1. Okay, and this one is actually a 5, right? And x is 30, y is 36 raised to the power 1/2. Delta y you still don't know. This one is your, this whole thing is your delta f. Okay, at this moment, your delta F at this moment, okay, with the increment of your skilled labor by 1. However, what you need is that you need your total output to be the same. So, well, I mean, it's pretty sad, but what will happen? Of course, the unskilled labor will be decreasing, is it? Because you already increase some worker, so some of the worker must be decreased, right? So if you need this one to be 0, okay, this is what, 60, this is 6, so it is 25, is that right? Delta y, so it means that your delta y is negative 60 over 25, okay, and this one is a what, 2.5, I mean 2.4, okay. So it means that to make the output to be the same, okay, we need to, of course, decrease the unskilled worker. The word decrease because of the negative, okay, by 2.4 hour. It's okay. I mean, it's sad, but this is what we need to do. Is that correct? Okay. So again, this is roughly speaking some information for you to decide whether you are going to whether you want to increase the skill labor or not, and you want to kill some of the unskilled labor or not. Okay, that's your own choice. Okay. Sometimes the change, okay, the change that you need to know, you need to do a comparison as well. So to do the comparison, usually we are talking about the so-called percent change, okay, the percent change. So the setting are the same, that your set is a function of x and y, and you got your delta x as an increment, a small change in terms of x. Your delta y is a small change in terms of y. The corresponding percent change in z, it is a delta z over z and multiplied by 100. So this is your simple formula, okay, just like this. Again, don't forget that your delta z is actually the z of x plus delta x and y plus delta y minus your z of xy, okay, but it can be approximated by this quantity, okay, it can be approximated by these two contributions added together, okay. So for example, if you're talking about the volume of the cylinder, okay, the volume of the cylinder is given by the pi r square h, of course, you know it, right? Where your r is the radius and the h is the height. So the cylinder look like this, okay. You got the height and the radius r, okay. You need to approximate the percent change by which the volume of the cylinder increase, okay, if the radius increases by 1%. So this is the increment in terms of your radius r, right? So what does this mean by increase by 1%? It means that your delta r over r, okay, multiplied by 100%, it is 1. And the height, okay, increased by 2%, so it means that delta h over h multiplied by 100% is 2. We get? So what you need to find is to find the percent change of the volume, okay. Of course it will be increased, right, because you got a bigger radius and a longer height, okay. So the higher height, so it must be increasing, of course. So what you need to find is to find the percent change in terms of z, okay. So as we told you that the delta z over z, of course, I mean, if you need it in percent, then you are going to multiply by 100. Okay, it is approximated by this is not the z, because now is about the volume, so you can use the v instead, so that it is coincide with the context. So it is a dv dr delta r and dv dh delta h over v multiplied by 100. Okay, so what was actually the v? The v is pi r square h. We get. So this one was your dv dr. So a derivative with respect to r, you have pi h, they are constant, and then a derivative go directly to your r square, so you have 2r, and then delta r. Okay, and this v can be, I mean, divided to separate your separate the fractions, just like that. Okay, and then add the dv dh. So now here your h is a variable, so you have pi r square, and the derivative go directly to your h, which is 1, and then delta h over pi r square h, and you are going to multiply by 100%. Okay, so if you look at it carefully, the pi cancelled, the h cancelled, and the r, one of them also cancelled. Okay, the pi cancelled, the r square cancelled. So what you end up with on this component is delta h over h, and this one, it is 2 delta r over 1 of the r. So let me just write down here. So you have delta r over r with the factor of 2 multiplied by 100. Okay, you see, and your delta h over h multiplied by another 100. Okay, this one is already there, right? Your delta r and r with 100, so you have 2 and 1. This one, the delta h over h and 100, you got a 2, so it is a 4%. Okay, so it means that the increment of increasing the percent change, okay, so the percent change of a volume, okay, is about 4% if your radius increased by 1% and your height increased by 2%. Okay, this is the effect. All right, so we are going to stop this clip right here, and we are going to see you later. Bye bye.